There will be 4 free response questions on the AP Precalculus exam. This video is modeled after FRQ 4, which is about trigonometric, exponential, and logarithmic equations. Let's pretend it's from the 2002 AP Precalculus exam. If you appreciate the content, please give it a like. Pause the screen to read these general instructions. Part A. The functions g and h are given by this expression and this expression. A Part 1. Rewrite g of x as a single logarithm base 10 without negative exponents in any part of the expression. Your result should be of the form log base 10 of expression. There is a property of logarithms that says if there's a number in the front, you can move it to the exponent to form an equivalent expression. So on the first step, I'm going to move this 1/2 to the exponent, and I'm going to move this 3 to the exponent. Another property of logarithms says that the difference of two logs can be equivalently written as the single log of a quotient. So the log of a minus the log of b is equal to the log of a over b. Similarly, the log of x to the 1/2 power minus the log of x to the 3rd power can be written as the single log of x to the 1/2 power over x to the 3rd power. We know that when you divide with like bases, you subtract the exponent. So we can simplify down to x raised to the power of 1/2 minus 3. To subtract 1/2 minus 3, we need like denominators. We can multiply 3 by 2 over 2. So this will be equivalent to 1/2 minus 6 over 2. 1/2 minus 6/2 is equal to negative 5/2. So far we have this. However, we need to rewrite the expression without negative exponents. The negative 5/2 power will drop this part of the expression down to the denominator. So g of x equals the log base 10 of 1 over x to the 5/2 power. A Part 2. Rewrite h of x as an expression in which cosine x appears once and no other trigonometric functions are involved. Looking at h of x, I can tell we're going to need some identities. Here is the set of identities I want you to memorize for the AP exam. Pause the screen and practice writing the identities from memory onto scratch paper. I think we are about to use this identity right here. We can use this identity to rewrite the numerator of h of x. So we have h of x is equal to, and instead of sine 2x, we can write 2 sine x cosine x. In the denominator, we still have sine x. But then we notice that we do have sine x in the numerator and in the denominator. These will cancel each other out, leaving behind h of x is equal to 2 cosine x. Are we done? Rewrite h of x as an expression in which cosine x appears once and no other trigonometric functions are involved. I think it's just that easy. Part B. The functions j and k are given by j of x equals this expression and k of x equals this expression. B Part 1. Solve j of x equals 10 for values of x in the domain of j. So we need to set j of x equal to radical 10. We begin with this. I'm going to do 2 things on the next step. First of all, when you multiply like bases, you add the exponents. So we will have 10 to the x plus 3 power on the next step. Also, let's add radical 10 to both sides of the equation. But radical 10 plus radical 10 is 2 radical 10. We need to solve this equation for x. That means we need to get rid of this base 10. And a base 10 can be canceled out with a log base 10. So let's take the log base 10 of both sides of the equation. On the left side, the log base 10 and the base 10 will cancel each other out, leaving behind x plus 3 equals log base 10 of 2 radical 10. Of course, we can get the x by itself by subtracting 3 from both sides. So we get x equals the log base 10 of 2 radical 10 minus 3. This is the solution. However, I'm afraid we might be required to simplify this a little bit. I see that we have log base 10 and there's a 10 here, so there is some simplification that can be done. One property of logarithms is that the log of a times b is equal to the log of a plus the log of b. So here we have the log of 2 times radical 10. This can be split up as the sum of 2 logs. We could write the log base 10 of 2 plus the log base 10 of radical 10. Instead of writing radical 10, I'm going to write 10 to the 1/2 power, which does mean the same thing. And then we have the minus 3. In this form, we can see that the log base 10 and the base 10 will cancel each other out. So on the next step, we will just have a 1/2 right here. The 1/2 and the minus 3 are like terms. We just need like denominators. We can multiply the 3 by 2/2. So this is really 1/2 minus 6/2. So that will be negative 5/2. So I think I'll keep you with me on this journey. So we have x equals the log base 10 of 2 minus 5/2. I'm not sure if you will get full credit if you stop here. So to be on the safe side, go ahead and simplify down to this. Just for fun, here's another way you could have solved this equation. The first couple steps will be the same. We multiply like bases by adding the exponents. So we have 10 to the x plus 3 power as before. Let's go ahead and add radical 10 to both sides again. So that makes 2 times the square root of 10. However, this time around, I think I will immediately rewrite radical 10 as 10 to the 1/2 power. That's because for this method, I want to turn around and divide both sides by 10 to the 1/2 power. So it would look like this. Let's divide by 10 to the 1/2 power here and here. So of course on the right hand side these will cancel each other out. On the left side we are dividing with like bases, and we know that when you divide with like bases you subtract the exponents. So we will have 10 to the x plus 3 power minus 1/2. And this will equal 2. So we just need to simplify the 3 minus 1/2 part. I think I will do that scratch paper style. If you felt like doing decimals, you could say 3 minus 1/2 is the same as 3 minus 0.5, which would be 2.5. So you could just put 2.5 right here. Nothing wrong with that. Or if you prefer fractions, you can multiply 3 by 2/2. So really we have 6/2 minus 1/2, which is going to be 5/2. On the next step, you will either have 10 to the x plus 5/2 is equal to 2, or you might have chosen 10 to the x plus 2.5 is equal to 2. Both work just fine. Either way, we can get rid of the base 10 by doing the log base 10 of both sides of this equation. On the left side, the log base 10 and the base 10 will cancel each other out. We are left with x plus 5 halves equals log base 10 of 2. Obviously, we can isolate the x by subtracting 5 halves from both sides. So we get x is equal to log base 10 of 2 minus 5 halves. And that's the exact same answer that we got by the other method. So you can choose whichever method seems easiest to you. B part 2. Solve k of x equals 5 pi over 3 for values of x in the domain of k. We need to set k of x equal to 5 pi over 3 and solve. Quick side lesson, a over b divided by c is equivalent to a over bc. In other words, if you divide a fraction by another number, whatever you are dividing by will end up multiplying into the denominator. And that's what we are about to do right here. I want to get rid of this 2 by dividing both sides of the equation by 2. But when I do that, I'm going to have this fraction divided by 2. And as I just demonstrated in the side lesson, this 2 is going to end up multiplying into the denominator. So on the next step, we will have 5 pi over 6. Next, we can cancel out the arc cosine by taking the regular cosine of both sides of this equation. So I can take the cosine of the left and the cosine of the right. So on the left, cosine and arc cosine cancel each other out. They are inverse functions, leaving behind negative square root of 4x. On the right side, we have the cosine of 5 pi over 6. Maybe I'll just show the extra step. But you should be able to tell me the cosine of 5 pi over 6 immediately. If you have not yet memorized the 9 trig values on this chart, you need to pause the video and memorize the chart right now. For the cosine of 5 pi over 6, the reference angle is pi over 6. And the cosine of 5 pi over 6 will be equivalent to the cosine of pi over 6, which is radical 3 over 2, except that it might be negative depending on the quadrant. We can think of pi as 6 pi over 6. Therefore, 5 pi over 6 is in the second quadrant, pi over 6 before 6 pi over 6. Cosine is the x value on the unit circle, and x values are negative in the second quadrant. So the cosine of 5 pi over 6 is equal to negative radical 3 over 2. Now we have negative radical 4x is equal to negative radical 3 over 2. Dividing both sides by negative 1 gives us radical 4x equals radical 3 over 2. Squaring both sides of the equation will get rid of the radical on the left. On the right-hand side, we square the numerator and the denominator separately. Squaring radical 3 leaves us with 3, and squaring 2 gives us 4. Finally, we will divide both sides of the equation by 4. Here's that shortcut again. We know that when we divide a fraction by an extra number, the number you are dividing by ends up multiplying into the denominator. So that's how we know it's going to be x equals 3 over 16. You don't need to show this. Just do that in your head. Kabam! Part C. The function m is given by m of x is equal to 3 sine squared x plus cosine squared x minus sine x. Find all input values in the domain of m that yield an output value of 2. This is a long way of saying set m of x equal to 2 and solve. I'm noticing that we have a combination of sine and cosine. It will be much easier to solve the equation if we can rewrite the equation to be either all sine or all cosine. Since 2 out of 3 of the terms involve sine, let's see if we can replace cosine squared x with an expression involving sine. If we go back to the identity sheet, I think we can use this identity to rewrite cosine squared in terms of sine. This identity appears the most often, so if you memorize only one identity, let it be this one. If we want to get cosine squared by itself, we would subtract sine squared from both sides of this equation. That will leave cosine squared x is equal to 1 minus sine squared x. So let's replace cosine squared x with 1 minus sine squared x. That will leave 3 sine squared x, and then here it comes, plus 1 minus sine squared x, and then picking up from here, minus sine x is equal to 2. I'm noticing that we do have like terms here and here. So 3 sine squared minus 1 sine squared will be 2 sine squared. So now we have this. To solve equations like this, we need 0 on one side. So let's subtract 2 from both sides, which will give us a negative 1. But as we rewrite, let's change the order to put it in a standard form. So we have 2 sine squared x, and then let's put the minus sine x in the middle, and then the minus 1 equals 0. Hopefully this will factor. Start with the first term. 2 sine squared x will factor as 2 sine x times sine x. Skip to the last term. Ignoring the negative sign for a moment, 1 will only factor as 1 times 1. When I'm factoring, I always say the following phrase to myself: inner plus outer must equal the middle. Here's what I mean. The inner terms are these two. If we multiply the inner terms together, we get sine x. Sine x is what I mean by inner. The outer terms are these two. 2 sine x times 1 is 2 sine x. So that's what I mean by outer. The inner plus the outer must equal the middle. In this case, the middle term is negative 1 sine x. We control the signs. What would the signs have to be for 1 sine x and 2 sine x to make negative 1 sine x? Well, if we had a positive 1 sine x and a negative 2 sine x, that would make the middle of negative 1 sine x. That's how we know we need a plus here and a minus here. Always check one last thing. Make sure you are getting the correct sign on this constant. Positive 1 times negative 1 is negative 1, so we factored it. We can finish solving by setting each of these factors equal to 0 and solving. However, I usually do this in my head. If we set 2 sine x plus 1 equal to 0, we will subtract 1 and divide by 2. So we get sine x is equal to negative 1/2. Setting sine x minus 1 equal to 0, we add 1 to both sides, and we get sine x equals 1. Ignoring the negative sign for a minute, we know that the reference angle for this first equation is pi over 6, because we have memorized that the sine of pi over 6 is 1/2. That's right here on the chart. By the way, when I say the reference angle is pi over 6, I'm talking about the angle between a terminal side and the nearest part of the x-axis. So on the interval from 0 to 2 pi, there are 4 angles with a reference angle of pi over 6. we want sine to equal negative 1/2. Sine is the y value on the unit circle, so we need to stick to quadrants 3 and 4, where the y value, and thus the sine function, will be negative. We can think of pi as 6 pi over 6, and we can think of 2 pi as 12 pi over 6. Therefore, this angle in the third quadrant is 7 pi over 6, and that's going to be one solution. X equals 7 pi over 6. And this angle in the fourth quadrant is 11 pi over 6. Pi over 6 before 12 pi over 6. However, we were told to find all input values in the domain of M that yield an output value of 2. M does not actually have any domain restrictions. So, we can get infinitely many solutions by taking any one solution and adding 2 pi to it, which would take us all the way around and back to where we started from. So, if we start with 7 pi over 6, we can get infinitely many solutions by adding 2 pi k, where k is any integer. Starting from the 11 pi over 6, we will get another solution every time we add 2 pi. So we can add all of the multiples of 2 pi by adding 2 pi k, where k is any integer. So these are the infinitely many solutions that we get from sine x equals negative 1/2. But what about sine x equals 1? Sine is the y value on the unit circle, and the only place on the unit circle where the y value is equal to 1 is right here at pi over 2 radians. So one solution to this equation is x equals pi over 2. But again, we will get another solution every time we add 2 pi. So we can turn this into infinitely many solutions by adding multiples of 2 pi. In other words, by adding 2 pi k, where k is any integer. Hey guys, don't forget to like and subscribe. But also, if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.